A PLC is made up of hardware and software. Hardware is the part of a system that you can see, and software is the collection of computer programs that control what the hardware does. PLC hardware also connects to other hardware, such as input and output devices and human-machine interfaces, HMIs. Although not in the accompanying graphic, a programming device can also be considered as PLC hardware, but it is only connected to the PLC when needed. Because PLC applications vary in complexity, there is considerable variation in the appearance of PLC hardware. In a typical application, small and medium-sized PLCs are often used to control individual machines or manufacturing cells. These PLCs typically communicate via a network to one or more larger PLCs that collect data and coordinate the operation of some or all of the system. Additionally, because the needs of customers vary, Siemens SIMENS PLCs are available as modular controllers, embedded controllers, or as PC-based controllers. Of these three categories, modular controllers are the most common and are the focus of this course. SIMENS S7 modular PLCs include a variety of models. For example, S7-300 and S7-400 PLCs have been in service for many years. More recently, S7-1200 and S7-1500 PLCs have been introduced. Regardless of the model, SIMENS S7 modular PLCs are optimized for control tasks and can be adapted to meet application requirements by adding modules. Typical PLC module types are CPU modules, power supply modules, signal modules, communication modules, and special purpose modules. PLC CPU modules all contain a microprocessor, which is an integrated circuit that runs the computer software, and memory circuits that store the user program and related data and may include a removable memory card. A CPU may also have an internal power supply that converts the supplied power to the filtered low-voltage DC needed by internal circuits. If the CPU does not have an internal power supply, a system power supply module is needed to provide power. CPUs typically have the following three operating modes. In the stop mode, the CPU is not executing the user program, and a new program can be downloaded to the CPU. In the startup mode, the CPU executes any startup logic if present. In the run mode, the CPU executes the PLC scan repeatedly. The specific mode the PLC is in at any given time depends on a software setting and whether or not a critical CPU error has occurred. In the event of a critical error, the CPU is designed to go into the stop mode. The current mode for S7-1200 and S7-1500 PLCs is shown by the CPU Run Stop LED. The current mode for S7-1500 PLCs is also shown on the CPU's integrated display. Modern PLCs use modules that have solid-state memory. The memory size for each type of memory is specified in bytes, with 1 byte equal to 8 consecutive binary bits. Because modern memory circuits can store a large number of bytes, the following metric unit prefixes are used to indicate memory size: kilo K, mega M, and giga G. There are a variety of solid-state memory types, but these are the most common types. Read-only memory, ROM, stores information developed by the PLC's manufacturer that cannot be changed. This type of memory is non-volatile, meaning that the information contained will not be lost in the event of a power failure. Erasable programmable read-only memory, EEPROM, is protected from unauthorized changes. EEPROM can be read from, but not easily changed. EEPROM storage is sometimes referred to as firmware. Modern firmware is often designed to be updated when required. This is also a non-volatile memory type. Random access memory, RAM, is also called read-write memory and is used for temporary storage of programs and data. RAM is volatile, meaning that information will be lost in the event of a power failure unless power to the circuits is backed up by a battery or charged capacitor. Flash memory is a type of electrically erasable programmable read-only memory, EEPROM. Flash memory is a non-volatile memory type that, among other things, is used for SIMENS memory cards. These cards are available in a range of sizes and can be used to store or transfer a PLC user program and associated data. PLC CPUs have a memory organization that defines the available storage for various types of information. PLCs of a specific model typically have a range of CPUs that vary in the amount of user memory available. Descriptions of user memory types vary from PLC to PLC, but the following user memory types are typical for SIMENS S7 PLCs. Load memory is non-volatile storage for the user program and related data. When a user program is downloaded to the CPU, it is first stored in the load memory area. This area is located either on a memory card or in the CPU and is maintained through a power loss. Work memory is volatile storage for some elements of the user program. The CPU copies these elements from load memory to work memory during program execution. This is volatile memory, so the information is lost when CPU power is lost, but is restored by the CPU when power resumes. Retentive memory is non-volatile storage for a limited amount of work memory information. Much of the data used by the user program is stored in data blocks in the program. However, CPUs have global memory areas that are accessible by the user program. These include input I and output Q process image tables and bit memory M. Some CPU modules have an integrated power supply for powering onboard circuits. However, some PLC models or configurations require a separate system power supply for this purpose. This system power supply converts the incoming power to filtered, regulated, low-voltage DC power. The system power is provided to a backplane that is common to multiple modules. Multiple system power supply types are typically available for a PLC model to match the input voltage, which may be DC or AC. System power supplies also have a power budget that defines the amount of power available for interconnected modules. A load power supply, also called a load current power supply, provides power to input and output devices as well as the related input and output circuits. In some cases, the load power supply also provides power to other PLC modules, including a system power supply module. The load power supply module, PM, for a SIMENS S7 1500 PLC mounts on the same mounting rail as other S7 1500 modules. Siemens also offers a variety of C-top power supplies for use with a wide range of equipment. PLCs have a variety of signal module types. Each module has multiple I/O channels, and each I/O channel connects to one I/O device. The number of I/O channels on a module varies with the module type. Some modules have both inputs and output channels. Each input and output channel on a module has an LED that shows the status of that channel. One or more additional LEDs show the status of that module. Signal modules of various types are interspersed as needed throughout a system. Each module is configured at installation, and this configuration includes the assignment of a module address. This address, together with the module type, also identifies the location of image table status bits for the connected inputs and outputs. As a result of this configuration, a discrete input, DI, or discrete output, DQ, is associated with a specific image table status bit, and this input and output status information is available to the user program. Because each analog input or output must represent any value in a range of values, each analog input, AI, or analog output, AQ, is associated with a word, 16 bits of memory. At one time, PLC communications primarily used networks designed by equipment manufacturers for their own equipment. As more control devices with built-in computers were developed, the need for common approaches for communications emerged. This led to development of a variety of field buses by industry associations. A field bus is an industrial network used for distributed control. One example of a field bus is Profibus DP, the leading field bus standard, which was developed by Profibus and Profinet International, PI. With the growth in information technology, IT, the need for control systems to communicate with IT systems increased. IT systems often communicate via Ethernet local area networks, LANs. However, the original form of Ethernet was not adequate for factory communication, so industrial Ethernet was developed. Profinet, which was also developed by PI, is the leading industrial Ethernet standard. A PLC CPU often has one or more ports for a specific type of network communications. For example, S7-1200 and S7-1500 CPUs have at least one Profinet port. When additional network ports are required, or when a different type of connection is needed, communication modules are added to the configuration. PLCs are very fast and have many types of signal modules, but some tasks require special purpose modules. Many of these modules are designed for closed-loop control applications, which involve controlling a process or machine in response to a feedback signal from a sensor. A closed loop may require a special purpose module because of the type of sensor, control device, or algorithm used. A control algorithm is a set of rules or calculations that define the control process. For example, the proportional integral derivative PID control used in many applications uses a control algorithm. In addition to closed-loop control applications, PLCs use special-purpose modules for counting or generation of high-frequency pulses. S7-1200 PLCs have integrated technologies for high-speed counting, measuring, proportioning, open-loop stepper motor control, and PID control, reducing the need for special-purpose modules. S7-1500 PLCs also have technology modules for high-speed counting and measurement applications.